look at your homework that I have assigned over the weekend. I hope everyone had a nice weekend. The weather was absolutely beautiful, at least. Um, so here we have acceleration versus time graph. Now, in order to find acceleration versus time, we have to understand how much the velocity is changing in given amount of time, right? So if you look at this acceleration versus time, right, it's telling us how much the velocity is changing in given time. So to find the velocity from the acceleration, right? I mean, we all know from going from velocity to acceleration, we have to find the slope of the velocity versus time. But going from acceleration to velocity, we have to find area, right? So from acceleration, right, to velocity, right, we must find area, right? Yeah, I'm being Asian here. There you go. So um, if we were to look for, right, the change in velocity from 0 to 1 second, we must find the area under the graph between the time axis and the graph itself, right? So here, let's define the time axis. Okay, time axis is right here at 0. Okay. Eh. So here's the time axis. Okay. Let's see if I can. So once we have this time axis, this change in velocity, I'm going to call that change in velocity 1. And then that is the area underneath this graph bordered by the time axis. Okay? And I'm going to consider this area here to be my delta V2, an area here to be my delta V3, an area here to be my delta V4. Okay? Now, let's find out how much velocity has changed from 0 to 1 second. So it starts at 0 meters per second squared, and then it goes, well, not goes, but it changes to 6 meters per second squared. So how much has my velocity changed when there was an acceleration change of 0 to positive 6 meters per second squared? Well, when we find the area under this graph, right, here is a triangle, so 1/2 base, which is 1, times height, which is positive 6, right? So here I have positive 3 meters per second, because this is seconds, this is meters per second squared, therefore one of the seconds cancel out, giving me meters per second. So that's easy, right? But how much change we could figure out. But where did it start? We have to have this initial parameter in order to get this thing started. All right, so this is very important when we were finding areas, because this gives us our starting point. Let's continue on. Let's find the change in velocity for the second part. Again, it's the area, and this area is just a rectangle, so it's base times height, so it's 1 times positive 6, and this becomes positive 6 meters per second is my change in velocity. Similarly, My change in velocity 3, again, is the area. And here I have 1/2, right, base times negative, right, 6, right? Oh, no, it's okay. I mean, it's just, let's just use 6 for now, okay? So here we have positive 3 meters per second. And then here is negative 6. So I'm going to put that up here. Delta V4 is again the area between the time axis and the graph itself. Therefore, 1/2 base times negative 6. And that is equal to negative 3 meters per second. All right. So here we need to define our time axis again. Okay. And this will be our velocity axis. And looks like we're going to go up like definitely positive like 12. So we're not going to have enough if we go by 1. So we're going to say 0 meters per second, right? Positive 2, positive 4, positive 6, positive 8, positive 10, positive 12, positive 14. Here we'll make a negative 2 and maybe negative 4 and so on. So our parameter that we start with, our initial condition is when time is 0 seconds, my initial velocity is at 0. So 0 meters per second at t is equal to 0. Then it changed positive 3 meters per second in 1 second. So from here, we changed our velocity to positive 3 meters per second from 0 meters per second. Therefore, we have one of these Johns. Yeah. Now next, it looks like we have a constant acceleration because it's a horizontal line from 1 to 2 seconds. And the constant acceleration will change our velocity from positive 3 to 6 more meters per second in the positive direction. So it'll be at 9 meters per second from 1 to 2 seconds. So from positive 3 to 6 more, we get positive 9. And this acceleration is constant, so this slope value better be constant. So instead of a curved line, in this case we have a straight line going from positive 3 to positive 9. So I use this magical device called ruler. Okay. And then I have positive 3, and my slope value goes to 0 at 3 seconds. So when I reach 12 meters per second, my slope value for my acceleration is 0. So my velocity value, right, should flatten out at 3 seconds. It should flatten out right here, right? So the slope value should be 0 at 3 seconds for my velocity value. So it flattens out here and it goes up 3, so it goes up to 12. So it should be doing one of these Johns. Yeah. Then we are going still in the positive direction, but our acceleration is in the negative, so we are actually going to slow down to positive 9 meters per second because we're going to go from 12 meters per second, slows down 3 meters per second. Therefore, we're going to end up at 9 meters per second from 3 to 4 seconds. So that's what it's going to look like. Okay. So let's ask some questions here. So I know most of you who had calculus knows that if we take a derivative of position versus time graph, we have velocity, right? And then if we take a derivative of the velocity function, we will have acceleration function. And then if we have a derivative of acceleration, what do we have? You guys remember? Anybody had poise? No? Somebody has hands up. Daniel.
Jerk.
Oh, you're calling me a jerk. Great. Now, Daniel is absolutely correct. Derivative of acceleration is called a jerk. And that's actual mathematical term. Um, when you have change in acceleration in given time, the motion itself is very jerky motion. It's not a smooth, constant acceleration motion. It's very jerky. Okay, so in this particular case, this motion itself is very jerky right here because it's not a smooth acceleration. It's very jerky. This is smooth acceleration because acceleration is constant. But here, jerky motion, as well as this. All right. That's why our velocity is going to be kind of be jerky here. That's why it's curved. Here, smooth acceleration, so it's nice and straight. Jerky motion as well here. All right. I don't know if any of you drive a stick shift. I mean, you all live on main lines, so like, you take your grandpa's 911 turbo out once in a while, just to open it up a bit so the oil circulates. When you actually go from 0 to 60 miles per hour in first gear, right? That's what you can do with 911 turbo. And then as soon as you pop in the clutch, right, you're going to get that little jerky motion going, right? And that's what that jerky motion is. So every time you switch gears, you're going to get that little bit of that jerky motion. All right, good. Let's see. What is the meaning of the slope of the acceleration graph? What does that mean? So when there's a slope, okay, so that slope of the acceleration graph represents the time rate of change of the acceleration. Okay. Which is called a jerk. And then I think derivative of jerk is like snap, and then derivative of snap is crackle, and then pop, and then surge, and all that good stuff. All right. B. Is the object speeding up or slowing down from 0 to 1 second? From 0 to 1 second, is the object speeding up or slowing down? Now you can look at either one of these graphs to answer that question. The easiest one will be looking at the velocity graph. Is the object speeding up, slowing down, or going at a constant velocity? What's going on? From 0 I mean, 1 to 2 seconds. 1 to 2 seconds. I start at positive 3 meters per second and I go positive 9 meters per second in 1 second. Jack, what would you say?
So yeah, from time 1 to 2, it would be moving at a constant rate because the slope stays the same.
But is it speeding up, slowing down, or is it going at a constant velocity?
Oh, constant. It's going at a, it's speeding up, right? To get
It is speeding up. So it is definitely speeding up from positive 3 to positive 9 meters per second, right? So it is speeding up, right? Going from positive 3 meters per second to positive 9 meters per second. All right. What about part C? Is the object speeding up or slowing down from 3 to 4 seconds? Ben?
It's slowing down.
It's definitely slowing down, right? So we go at 12 meters per second, right? At 3 seconds, and then we slow down to 9 meters per second, right? So it is definitely slowing down, right? Let's ask more questions. Ben, you have a question?
Yeah, do you want us to write what the change is like going from 3 to 9 or 12 to 9
Yeah, it'd be nice
for the
to.
answers?
Yeah, it'd be nice to show me that you really understand. But if you're not sure, then don't write it, right? But if you really want to show off, yeah, I would definitely write that. You know. Here's a question for everybody: which way is the object moving from 3 to 4 seconds? Is it positive direction or negative direction? John, positive direction. Yeah. Does this object ever go in the negative direction whatsoever? Ben?
Oh, no.
No, it does not. Because look at the velocity values right here. They're all positive velocities. So there will always be positive direction, right? There were positive. It's just always going in a positive direction. Okay. All right. Good. Very good. All right. I assigned this. This is going to be very similar to your quiz coming up on Thursday. So if you could do these 2 pages, pages 4 and 5, you should be fine with your quiz. Okay. So let's take a look at page 4. Okay. All right. So first, let's identify where our um, time axis is going to be. So here's my time axis right here. Now make sure you understand what graph this is. This is velocity versus time graph. Okay, so some people get this confused. Like, I thought this was position versus time. No, you got to read this. Okay, so from velocity versus time graph, if we want to go to position versus time, what should we do? From velocity versus time graph to position versus time, what should we find? Henry?
you gotta find the area.
Area. I like that. So from velocity to position, right? must find area. Okay? Area. So if we were to find the area between the time axis and the graph itself, okay, this here, we'll consider that to be my change in position x1, right? And my change in position x1 here can be calculated by finding this area right here. So my change in x1 is equal to area. And that is, right, 1/2 base times the height, which is -4. Therefore, it is -2 meters. Well, this is easy, right? But delta x2 is 0 because there is no area. Okay? What about my delta x3? I mean, I'm not gonna write down all this for you. You should know, right? So it's 1/2 base times height. So this looks like positive 1.5. Are we okay with that, meters? And then my delta x4 here is also positive 1.5 meters. Delta x5, right, is equal to negative 1.5 meters. And my delta x6 is this whole thing right here, which is negative, right, 3.0 meters. And delta x7 is negative 1.5 meters. And my delta x8 is equal to 0 meters. Everybody okay with that? If you have any questions, stop me now. All right? Now, we know it changed 2 meters in the negative x direction from 0 to 1 second. But we got to know our starting point, or the starting point is the important part to start. And if we don't know where to start, we can't really do this. If this wasn't given, I guess you could assume it starts from 0. But since it's given to us when t is equal to 0 seconds, it starts at positive 2, okay? We can say, oh, at 0 seconds, it starts at positive 2 meters. So this thing's already cheating, right? It's not starting from the starting point. It starts from positive 2. Then it travels 2 meters in the negative x direction. So again, here is my time axis. I gotta always have my time axis here, I guess. So here's my time axis. Got stuck on that camera. So here's my time axis, and I am traveling 2 meters in the negative x direction. So 2 meters, I end up at 0. And my velocity approaches 0 at 1 second. So after I travel 2 meters in the negative x direction, it should stop. So my slope value at 1 second should be 0, which is flattening out here. So it's going to be one of these. Now, as far as like the curviness, just fake it. Make it look pretty, okay? You don't have to make it like, is it really curvy like this, Mr. Game? Or is it like, you know, I don't care. Just make it look pretty, all right? All right, now, from 1 to 2 seconds, you know, I didn't go anywhere. It's 0 meters per second. So And it's also 0 meters traveled. So I stay at my origin. Then it travels in the positive direction 1.5 meters in 2 to 3 seconds. So I end up here, and 3 to 4 I go positive 1.5 more, so I end up here. So this here looks like it is speeding up. So my slope value is going to be increasing, increasing, increasing. And here my slope value is going to be decreasing, decreasing to 0 at 4 seconds. So this is going to be flattening out. So it's going to be one of these. Then I travel 3 meters in the negative x direction. Right? I'm sorry, I skipped this. Sorry. I'm traveling negative 1.5 meters, right, from 4 to 5 seconds. So from 3, I ended up back at positive 1.5 because I'm going negative 1.5 meters from positive 3. So here is what I get. Then from 5 to 6 seconds, I travel negative 3 meters. So 1, 2, 3. So I ended up beyond my starting position. And look at this, I'm going at a constant velocity of negative 3. So my slope value should be constant value of negative 3. So I use this magical device called a ruler to draw a straight line. Then it continues to travel in the negative x direction, okay, for 1.5 more meters. So I ended up here at negative 3. And notice my value for the slope should be 0 at 7. So this should be flat. So it's going to be one of these. And then I didn't go anywhere for 7 to 8 seconds. So I stayed at negative 3. So that's how I transpose from my velocity versus time graph to the position versus time graph. All right. All righty. Now, I'd like to go from velocity versus time graph to acceleration versus time graph. So to go from velocity to acceleration, I should find the slope, right, of the velocity versus time. So when I look for the slope here, right, my acceleration 1 is equal to, now this is 0 minus negative 4 over 1. So 0 plus 4, so it's 4, positive 4 meters per second squared. My A2 is 0. My A3 is 3 minus 1, right? Divide by 1, so it's positive 3 meters per second squared. Here, my A4 is 0 minus 3 divided by 1, so it's negative 3 meters per second squared. And so is my A5, which is negative 3 minus 0 over 1, so it's also negative 3 meters per second squared. My A6 is 0. My A7 is 0 minus negative 3, right? So it's positive 3 meters per second squared. And my A8 is 0. So now if we want to graph these slope values onto my acceleration, so notice how the slope values are constant. That means my acceleration values between those time intervals should be constant functions, which are horizontal lines. So here's my time axis again. Okay. So from 0 to 1 second, it is positive 4 meters per second. So from 0 to 1 second is positive 4 of a constant slope value of positive 4. Then from 1 to 2 seconds, my slope value is 0. So my acceleration value is also 0. Now I know somebody's going to ask me,
Yo, Mr. Kim, shouldn't this be open circle and this should be closed circles to be a proper function so it doesn't fail the vertical line test?
yeah, if you really want to do that, I guess you can make this open and you can make this closed. You know, and then you could put a dotted line down here if you really wanted to. Yeah, sure. Ramdan, you have a question?
So on the quiz on Thursday, will we have to put in the open circles and closed circles?
No, you don't have to. You don't have to. I mean, you can if you want to, but make it look pretty. If you don't make it pretty, I'm going to be angry. All right? Make your open circle like really open and then closed circle closed. All right. Any other questions? All right. So next, here from 2 to 3 seconds, it looks like we have 1.5 meters per second squared is the slope value, and it is constant. So we'll make, right? I'm sorry, 3 meters per second squared, not 1. So 3 meters per second squared of constant acceleration from 2 to 3. And then from 3 to 4, negative 3. And 4 to 5 is also negative 3. So voila. Voila. And then 5 to 6 is 0. Right? I'm going to put 0 here. 6 to 7 is positive 3. Right? And then 7 to 8, 0. Voila. All right. Hopefully you should be able to do that on Thursday. Okay? Hopefully you should be able to do that on Thursday. So we should be able to now answer some of these questions using these graphs. Okay? So let's take a look at this graph of velocity versus time, then position versus time, and acceleration versus time. Most of these can be answered just by looking at the velocity versus time graph. All right, so keep this thing out, but let's take a look at the questions in the back. Here it says, what distance did the object travel from 0 to 4 seconds? Now, you have to know the difference between, distance and displacement. I think I told you that like earlier, right? That you have to know the difference between distance and displacement. So distance, we really don't care about which direction it travels, right? So for distance, right, we just add up all the change in positions in a positive values. So here we get -2 meters in the absolute value, plus 0 meters in the absolute value, right? And then we have positive 1.5 meters, plus positive 1.5 meters, right? And then if we add them all up, we just get 5 meters. That's it. No direction, right? No x hats, just 5 meters. It will always be positive. What about the distance from 4 to 8 seconds? Again, the distance, right, from 4 to 8 seconds is, right, we have negative 1.5, but still we'll keep that as positive because it's in absolute, right, plus absolute value of -3 plus absolute value of -1.5 plus 0, and we should get 6 meters as our answer. All right. Next. What is the displacement between 0 to 4 seconds? Now it's a different story. Now, displacement itself, this must, right, have direction. So you have to have positive and negatives. So here, 0 to 4 seconds, I have -2 meters, right? X hat, plus 0 meters x hat, right? Plus 1.5 meters x hat, plus 1.5 meters x hat. So when I add them all up, I get positive 1 meter x hat as my displacement or change in position from 0 to 4 seconds. All right, and then what is the displacement from 0 to 8? So, well, that's easy now, right? So here I have all this, right? So I'm going to write all that down again. So -2 meters x hat plus 0 meters x hat plus 1.5 meters x hat plus 1.5 meters x hat, right? And then we have minus 1.5 meters x hat, right? Minus 3 meters x hat minus 1.5 meters x hat, right? Plus 0 meters x hat. Okay. So if you work it all out, you're going to get -5 meters x hat as my change in position from 0 to 8 seconds. All right. So what about letter E? What is the average acceleration of the object between 3 to 5 seconds? Well, let's take a look at the velocity versus time graph. From 3 to 5 seconds, I want to find out what the average acceleration is. So I'm looking for a slope between these 2 points. And it looks like we already know what that slope is because it was calculated already to be -3, right, meters per second squared. So the average acceleration from 3 to 4 seconds, right, is equal to, right, change in velocity over change in time. I'm sorry, 3 to 5 seconds. Sorry, 3 to 5 seconds. So change in velocity, which is VF, which is at 5 seconds, minus VI, which is at 3 seconds, over T5 minus T3. So here I have negative 3 meters per second, right? X hat, minus positive 3 meters per second, X hat. Whole thing over 5 minus 5 seconds minus 3 seconds. So this gives us negative 6 meters per second x hat over 2 seconds. Therefore, negative 3 meters per second squared x hat is the correct answer. Nikita, you have a question?
Yeah, I have a question about the displacement question.
Okay.
Well, why can't we use the position versus time graph and do final minus initial to find the displacement?
You could do that.
Oh, okay.
Yeah, there's plenty of ways of doing that, and that's another correct way of doing it. Correct. Yeah, if you're more comfortable using position versus time graph, absolutely, you can definitely do that.
Okay, thank you.
Yep. Any other questions? All right. Last but not least, F. Let's take a look at F. Now, F, average acceleration from 5 to 6, right? So if you were to look at the velocity versus time graph again, 5 to 6, it looks like it is 0, right? Because it's a flat line. So average acceleration from 5 to 6 is equal to, right? Again, delta V over delta T, and that is, right, negative 3 minus negative 3 over, 6 minus 5, and that is 0 meters per second squared. Except, I know somebody's going to, yo, Mr. Kim, since it's 0, do we really need to put like meters per second squared x hat? Yeah, it is technically correct by putting it in. Jack, you have a question?
Yeah, would we like typically need to show our work for that?
No.
No labeling for it, but it's like
I know, it's so obvious, right?
yeah.
Yeah, I'm not going to insult your intelligence by you not showing me work, and I'll take points off. I won't do that to you. All right. All right. So let me see. Let's take a look. Um, what if I ask you a question like, what is the average acceleration from 0 to 3 seconds? Ben?
Would it be 7/3 meters per second squared?
Positive or negative?
Positive.
Excellent. That is correct. So all you have to do is just find the slope of these two, right? And booyah, you should be able to get your average acceleration from here to here. Right? Good. How about another question? What is my instantaneous velocity? What is my instantaneous velocity at half a second? Henry?
Would it be -2?
Negative 2 what? Bananas per boats?
-2 meters per second.
Good. Negative 2 meters per second. Which way?
Positive.
Positive. Which axis?
The x-axis.
X axis. So you have to give me those components for velocity.
Wait, so does velocity need the x hat?
Yep. Speed, you don't.
Okay.
So if I ask you what is the instantaneous speed at half a second, then you just say
-2 meters per second.
not negative, just
Oh, 2.
2 meters per second, because that's how fast it's moving. Because speed doesn't really care about which way it goes or which axis it goes. It just says 2 meters per second. All right. However, if I ask you for instantaneous velocity at half a second, then you have to say -2 meters per second x hat. Cool?
Yeah, cool.
All right. 5.5 seconds. Is the object moving or not moving? Shreya, is it moving?
Yes.
Yes. Which way is it moving?
In the negative x direction.
How fast is it moving?
-3 meters per second.
All right, fair, okay, that's fair. It's just 3 meters per second. And then I was going to ask you which direction is going to, all that stuff. But you see how we can look at this graph and tell the motion exactly what's going on, right? All right. So make sure you understand that. Which direction is the object moving at 6.34 seconds? Which direction is the object moving at 6.34 seconds? People are panicking, like, wait a minute, 3.4. Shreya?
Negative x direction.
Negative x direction. Very good. Is it speeding up or is it slowing down at 6.34 seconds? Shreya?
Speeding up.
Is it speeding up? Jack?
Wouldn't it be slowing down because it's going towards the 0?
Absolutely. It is actually slowing down. Okay? It is slowing down because the slope from 6 to 7 seconds, even though it's positive slope, it's going in the negative direction. So it is definitely slowing down going in the negative direction. So make sure you see that. Okay? That's very important. All right, I think you should practice that because that's very important. Those questions are going to be asked. Okay. All right. I'm going to give you guys about a minute to see if you guys can bring an empty or blank sheet of paper or papers. I'm going to be going over some equations with you guys that you're going to need in order to solve the other problems. So before I move into other homework problems, such as your multiple choice questions and those free responses in the back of your summer review packet, I'm going to derive some important equations for you guys. And hopefully this will help you understand it deeper when we solve these constant acceleration problems. All right, so get a blank pieces of papers out, and then I'm going to see if I can do this off the top of my head, and then we'll do this. All right. I like using graph papers for some reason. I know there are a lot of lines there, but I don't know. I think it's pretty cool. So here we go. Ready? I'm going to start with a definition of acceleration versus acceleration. Just mathematical definition of acceleration. All right? So here we go. Acceleration is defined to be the time rate of change in velocity. Okay, so for now, I'm just gonna drop this this vector symbol for, it may get dropped because sometimes I write fast. And so this is VF minus VI, and they are vectors, okay, over TF minus TI. Now, most of you, when you use your stopwatch, hopefully you start your stopwatch from 0.0000, right? I know some of you will say, no, Mr. Kim, I don't like that number, so I like to start from 4.2 all the time. So whenever I get a time, I just subtract 4.2. Yeah. No, it defeats the purpose of a stopwatch, right? So if and only if, now that's what definition if and only if, right? So if and only if. This is a mathematical statement. If and only if, right? T initial is equal to 0, then delta T is just T final, or just T, okay? So if this is true, then I'm going to say my acceleration is equal to VF minus VI over T. So if I rearrange this equation using algebra and multiply both sides by time, I get A times T is equal to VF minus VI. So if I solve for VF and flip this equation around, I get VF is equal to VI plus AT. This equation is equation number 1 for constant acceleration equation. Sometimes in your textbook, this can be written as V is equal to V naught plus AT. This is VF and this is V naught. Same thing. Okay? Then, I'm going to talk about the average velocity. Well, average velocity, we defined it as change in position over change in time. Right? So, again, if and only if, right, T final is equal to, T initial is equal to 0, then delta T is equal to T final, which is just T. Then I can say average velocity, right, is equal to delta X over T. How do you find average of two test scores? Come on, how do you find, yeah, add the two test scores and divide by 2, right? So if I have two velocities, I add the two velocities and divide by 2 to get my average velocity as well. So if you look at this, they're identical. That means these are also identical. So I can set them equal to each other and say my delta X over T is equal to, right, VF plus VI over 2. So if I multiply time to both sides, I get delta X is equal to, right, VF plus VI over 2 times T. This is my equation number 4, which is trivial, but is very important equation actually. Sometimes this equation can be represented as follows. X final is equal to X initial plus VF plus VI over 2 times T. Same thing, they just split the delta X up into X final minus X initial. Okay? Now, let's take a look at, somebody should be asking like, yo, Mr. Kim, what's going on with like number 2 and 3? Yeah, we're gonna get to that. All right, because I did 1 and I did 4. There has to be 2 and 3 in between, right? And that's what we did for senior prank at St. Joe's Prep, right? You get like, you can't do this now because you know you get like animal cruelty, like, and all these people. You get like a greased baby pig. You number it like 1, 2, and 5, and let it loose. There's only 3, right? So you got 1, 2, and 5. Let it loose, and of course everybody's trying to chase it down, and they got 1, 2, and 5. They're looking for 2 and 3 like the whole day. They can never find it. You know, it's great. That's the best thing ever. All right, don't do it, please. All right, here we go. So let's take a look at when we can utilize these two equations. Okay, so here, if we were to say, I'm going to use equation 1, which is VF is equal to VI plus AT. And I'm going to use equation 4 and then put them together. So delta X is equal to VF plus VI over 2 times T. I will substitute this, which is VF, into my fourth equation, and let's see what we get. So my delta X is equal to, right, VI plus AT, right, plus VI over 2 times T. Then delta X is equal to, well, I could add these two VI's, and I get 2 VI's, right, plus AT, whole thing over 2 times T. Let's split these up and distribute this T through. So my delta X is equal to, right, I have 2 VI over 2 times T plus A times T squared over 2. So notice how these 2's can cancel out. So my delta X is equal to VIT plus 1/2 AT squared. This is my equation number 2. Sometimes this equation can be represented as X final is equal to X initial plus VIT plus 1/2 AT squared. In other textbooks, it can be represented as X is equal to X naught plus V naught T plus 1/2 AT squared. They're same things, okay? They're same things. All right, so one more. Let's do, again, equation 1, which is VF is equal to VI plus AT, and equation 4, which is delta X is equal to VF plus VI over 2 times T. I'm going to solve for time. So VF minus VI is equal to AT. So my T is equal to VF minus VI over A. So I will substitute this into my equation 4. Then what do I get? I get delta X is equal to VF plus VI over 2 times, right, VF minus VI over A. Well, if I multiply the bottom through, I get 2A, and then bring it to the other side, I get 2A delta X. is equal to VF plus VI times VF minus VI. Curses, foiled again. Right? Yeah, we have to foil this sucker. We know how to foil, right? And since these are, plus and the minus, that's pretty much the identity of difference of squares, right? So, if I rearrange this, my VF squared is equal to VI squared plus 2A delta X. That's my equation number 3. Again, this will be represented sometimes depending on which textbook you use in college. It'd be V squared is equal to V naught squared plus 2A delta X. Now don't forget, this delta X is X final minus X initial, okay? So sometimes they define this as also as follows. So don't get freaked out when you see this. They're the same things, okay? Okay, got that, everybody? So here, we got a bunch of equations. So let's put these together in a nice, concise form. So we know 4 equations we just derived. Equation 1, which happens to be VF is equal to VI plus AT. And our second equation was delta X is equal to VIT plus 1/2 AT squared. The third equation is VF squared is equal to VI squared plus 2A delta X. Fourth equation is delta X is equal to VF plus VI over 2 times T. Now, if we look at these 4 equations, there are five unique variables, okay? There are 5 unique variables. There are 5 variables. That is VF, VI, A, T, and delta X. And each of these equations, they only have 4 variables. So for example, the first equation, we are missing delta X. So when you are reading a problem and they don't say anything about delta X whatsoever, but they give you like 3 out of these 4 variables, then you use equation number 1. For equation number 2, VF is missing. So if they don't tell you anything about your final velocity, or then use this. This equation 3, you're missing time. So when you don't have time, you use equation 3. That does not mean you use equation 3 when you're running out of time at the end of the period while you're taking the test. That's a different thing, right? When you don't have time versus when you're running out of time are 2 different things, right? The time variable. Here, you're missing the acceleration. So you have to have a strategy when you are working these problems out with the constant acceleration equations. First, you should read the problem, right? People don't read the problem. They're just like, oh my God, it's a problem. Like they just like to just look at the numbers given to them. No. First, read the problem. Then, draw a small diagram or something, so you could understand it visually, what's the problem is stating. Then, third, write down all the givens. If there's one object traveling, just write down all the given variables for that object. Write down these 5 variables, and then whatever's given to you, write down the actual numbers next to those variables. And if you're looking for certain ones, you put a question mark down, and then if they don't even mention it, then you don't even have to write that variable down. Then you look for the proper equation that you can use after you know these, right? Then you can plug and chug. Okay? So you have to really, get used to these. So this is going to be your bread and butter from now until you graduate, or now until you take the finals. So these 4 are very, very important. So I would commit these 4 equations to memory. All right. I know, I don't know how this AP test is going to be happening towards the end of the year, but usually I tell my students to memorize the equations, because I know they give you the equation sheet, but the equation sheet they give you is like nothing compared to what you need to know. So if you're going to rely on those equations on the equation sheet, game over, right? Another thing is, if you are looking for equations on the equation sheet during the test, that means you're not going to have enough time to finish. All right? So that equation sheet is pretty much useless. So it could actually give you some kind of confidence by going back and check if you got your equation correct. But other than that, I would not recommend using that equation sheet whatsoever. All right? So, now that we know that, any questions? So, are you okay with all the problems that we did for this review packet? Did anyone have any questions? Are we okay with the Austin Powers and Dr. Evil and Mini-Me? Ben, you have a question?
Yeah, it was for one of the multiple choice questions.
All right, let's take a look at which one. Number 6? Number 5?
Yeah, is it, because it says it's dropped from the platform moving downward at 1 meter per second. Is that, I'm confused about, I'm assuming it's the acceleration of gravity is for the problem, right?
Correct.
So, do you just ignore that 1 meter per second if the platforms drop that?
Yeah, let me take a look at that. Let's see.
Of how, the 1 meter per second applies. Because it says the ball's dropped from the
Okay. Okay. Let's read this question. Let's read this question carefully. First, it states here that ball is dropped from rest. Whenever things are dropped, the initial velocity is 0 meters per second. So you have to think about what's given to you in this problem. All right, it is dropped from rest. It's moving vertically. So when things are moving vertically, maybe I should write that down here. When things are moving vertically, we're going to consider up direction positive, down direction negative. And also, when things are dropped, that means initial velocity is 0 in the y direction. When things are moving vertically on Earth, the acceleration in the y direction is g, which is negative 9.8 meters per second squared. That assumption is always good. When object is thrown upwards at maximum height, your velocity at y max is 0. Because when things are thrown up, it slows down, stops instantaneously before it speeds up, going back down again. Okay? So these are really important things to know when things are moving vertically up and down. Okay? So, let's take a look at number 5 again. From a platform moving downwards at 1 meter per second. So you are on a platform moving downwards at 1 meter per second, and you are dropping a ball.
Oh, so it has initial velocity of -1 meter per second.
There you go.
Okay.
You got it.
Yeah.
See how important it is to read the problem. I know it sounds kind of silly.
By the wording, 'cause the dropped at rest and then the platform.
Yeah. It is tricky, isn't it? So yeah, you have to really read it carefully. First of all, these problems are not written by English teachers. They're written by physics teachers and physics graduate students. So their English may not be perfect, okay? So you really have to read it carefully word for word because they're sneaky. So since it's already moving in a moving platform down, so this actually goes out the window. When you read the whole problem, your initial velocity is -1 meters per second. This, it strikes the ground at 125 meters below. This is important. So here's 125, here's 0, right? And it is moving downwards, right? So what is my delta y in this case? My delta y is y final minus the y initial. Here's my y final, here's my y initial. It is 0 minus 125. Therefore, my delta y is equal to -125 meters. That way, your time does not come out to be negative. Because if you don't have that -125 for your delta y, your time most likely going to come out to be negative. And that's either you should win a Nobel Prize for that, right? For inventing a negative time or time machine, or it's probably wrong. Chances are when you get negative time, that means you're wrong. Right? Does that pretty much set you up in the correct direction, Ben?
Yeah, that's exactly it. I just got kind of tripped up by the dropped at rest and then moving downward at 1 meter per second.
Excellent. All right, good. So for other people, like let's think about this. Here's how I would. Yeah, Shreya, question.
I did a question about a different problem.
Okay, we'll get to you. Nikita, you have a question?
There was also a different problem.
Okay, fine. So let me just help set up really quick, and then we'll move on to Shreya, and then we'll go to Nikita. All right. So here, I would write the variables that I know. So initial velocity, -1.0 meters per second. I always know gravity for Earth is -9.8 meters per second squared. And the reason why it's negative is gravity sucks. It always sucks towards the center of the Earth, right? Therefore, it's in the downward direction. That's why it is -9.8 meters per second squared. Okay? Then we also know my delta y, which is -125 meters. And what am I looking for? I am looking for time, right? Time. So notice I have 4 variables here, right? VF is not even given to us. So I could say, oh, VF is not given. I have 4 variables. I know my variables here. I could look for my time. Boom. See how that works out? Okay. All right. Good. You're probably going to have to use quadratic formula for that, right? Yeah. All right, Shreya.
So I just had a question on 10.
Number 10. Okay. Anybody else before 10? Nikita, what question did you have on?
Which equation did you say we were supposed to use for that last one?
For number 5?
Yeah.
I would say I would use equation 2 because I know my initial velocity, I know my delta y,
Yeah, alright.
And then-
I thought you pointed to number 3, and I got confused.
oh, no, you're looking for time, dude, so,
Yeah, I know.
Right.
That's fine.
yeah, so, yeah, I would use 2.
Alright, cool.
Nikita, you had a question? Which one did you
No,
have?
mine is 11.
11, all right. Kate,
Mine was number 6.
number 6, okay. So let's take a look at number 6. Here we go. Elijah throws a tennis ball vertically upwards. The ball returns to the point of release after 3.5 seconds. So what do we know? We know that ball is going to go up and it's going to come back down, right? What is the speed of the ball as it is released? Well, what do we know about this? Okay, let's write down everything we know. We know it's thrown vertically, so we have to say my acceleration is g, which is negative 9.8 meters per second squared. Yes? What else do we know?
That it goes like up and back down to where it started in 3.5 seconds.
Right. So t total is equal to 3.5 seconds. Now, what happens to something when you throw up in the air? When you throw something up in the air, right? What happens to the object, Kate? It goes up, it goes up. As it goes up, what happens to the object?
It gets slower and then it stops momentarily and then goes back down.
Excellent. So when it stops at the maximum height. Does that make sense? So what happens when it reaches maximum height? It stops instantaneously before it speeds up again back down, right? So we can do this 2 ways. We can do this where this is the initial. This is the initial and this is the final. Okay? And then we can find the VF to be 0 here.
Yeah.
How much time will it take to go from here to here?
Well, that's where I got confused because I thought it couldn't be just half of 3.5
It is
seconds.
exactly half
It is?
because it's a symmetrical.
But doesn't it go faster on the way back down because the
Nope.
acceleration of gravity is going with it?
Acceleration of gravity will be slowing this thing down just as much as acceleration of gravity will speed this thing up.
Oh, okay.
Because
That's where I got confused.
yeah, it acts on it with no prejudice whatsoever, whether it's going up or down. It would slow it down the same rate as it speeds it up on the way down, right? So every time you throw something up in the air, it's going to slow it down at 9.8 meters per second squared. When you are dropping something or when it's on the way down, it's going to speed it up, going 9.8 meters per second squared downwards.
Okay.
Does that help?
Yeah, I just got confused because I thought that it couldn't be half of the time, so then I didn't know where to go from there.
It is
But now
exactly
that
half.
makes sense.
Now, there's another way you could go. I start here, it goes up, and it comes back down. Right? What's my change in position? What's my delta x or delta y?
0.
0. I can use that too. Okay? So I can probably use either one of those information given to us to figure out my thing. All right? Give it a shot. And number 10, right? Number 10, I gotta find 10. All right, number 10. What's number 10? Somebody read it.
What is the velocity of the object at t equals 7 seconds?
All right, so what is my velocity? So what am I looking for? At 7 seconds, which is right around here, right? How do I find velocity from position versus time graph?
Find the area.
Hmm?
You find area?
Position versus time graph?
Oh, wait, no. You find the slope, I think? Sorry, I'm confused.
Yeah, I don't like this question because it seems like it's asking for is it, first of all, is it moving at 7 seconds? Who asked this question?
I did.
Is it moving at 7 seconds?
No.
No. So what's my instantaneous velocity at 7 seconds if it's not moving?
0.
0. So the answer here is wrong.
Oh, okay. I had that down.
Yeah, so that's a wrong answer.
Oh, okay. Yeah, I was gonna ask about that.
Yeah, that's
Wait,
a
how
wrong
did I-
answer.
How is it not moving? I think the scale is shifted to the right. Is the
It's because it's not moving because that's
the number?
It hasn't.
Wait, isn't the first vertical line
Because
5?
like the numbers aren't lined up.
Oh, is that what it is?
Yeah, the scale
I think
isn't
it's-
on the.
Doggone it. So are they saying this is 5 here?
Yeah.
Oh, all right. Forget it.
Confused.
Never mind. All right, then if that's the case, if this is 5, if this is 10, if this is 15, 20, 25, 30, now it's a different story. Now you have to find the slope of this. Right? Now find the slope at 7, which is around here somewhere. So if I were to find the slope between 5 and 10, I think that would pretty much handle it. Does that make sense? All right. So here, my V average between 5 to 10 is the instantaneous velocity at 7 as well. Or anywhere between 5 and 10 seconds, my instantaneous velocity is same as my average velocity. Therefore, -5 minus 10 over 10 minus 5. Okay, so we should have -15 over 5 or -3 meters per second is what it should be. So the answer is correct then. Sorry. Never mind. All right, is that okay? Jack, you had a question?
No, sorry.
Okay. All right. Is that okay? Who asked that question? Shreya? Okay.
Yeah, I didn't know.
Yeah, sorry. That is messed up, huh? All right, Nikita, 11?
Yeah, it was 11.
All right, 11. So what is the acceleration of the object at t is equal to 7 seconds? Well, this looks like it's moving at a constant velocity, right?
Yeah.
If it's moving at a constant velocity, is there a change in velocity?
No.
No.
So acceleration should be 0.
So it has to be.
I just want
Yeah, that is exactly why. Because if there's no change in velocity, there's no acceleration. You have to stay with the rule.
Thank you.
You're welcome. All right. Um, what time is this period over?
11:03.
Oops, I went over 4 minutes. I'm sorry. I'll take that 4 minutes back on your quiz. No, just kidding. I'm not going to do that. Well, when we're having fun, it's having a great time here. So we didn't know the time was flying that fast. So I'll stop here today. All right. On Thursday, we will go over some problems like free response questions if you want to ask any questions. And then we'll do a graphing quiz towards the end of the class. Is that fair? Is that good? All right. I'm going to grade it in 3 ways. I'm not going to try to nitpick. I'm not trying to punish people. If you hand in a blank quiz up, I mean, like, if you give me an answer with polar bear in a snowstorm with eyes closed, I will still give you half of the credit. All right? Because I'm a giving tree. If you have it perfect, I'll give you a perfect score. If you have anything wrong anywhere, I'll give you 80%. Got it? All right? So keep that in mind, and then we'll go from there. All right. Yeah, Jack?
Yeah, I just had a quick question.
Yeah.
You have to do like scientific. No, wait.
Sig figs?
Sig figs, yeah.
Dude, I hope you guys know how to do sig figs. If you can actually just round your answer to 2 decimal places, I'll be happy as a clam with a pearl. All right?
Sounds good.
Well, somebody's supposed to say, Mr. Kim, clams don't have pearls, oysters do. And then I'm supposed to say, well, duh, that's why I'm happy. All right, never mind. Get out of here. Go home.
Alright, thank you.
Thank you.
All right, if you have any questions, remain behind. Stay behind. All right?
Thank you.
All right.
Thank you.
All right. My mouse is not working.